So welcome to everybody. Good afternoon. It's my pleasure to introduce you, Christine Muschik. She's professor now in Institute for Quantum Computing at the University of Waterloo. I just give you an overview of his vita. She did a PhD with Ignacio Cirac at the Max Planck Institute in Munich. Then she did a postdoc at ICFO in Barcelona. And then another postdoc, as far as I understand, with Peter Soller in Innsbruck. Then she moved to Canada, and now she got a position there as a professor in Waterloo. She has a very good, a lot of papers and very good papers, and she has a lot of hours. I'm just going to tell you the last two ones. So she received the Emmy Noether Fellowship in 2018 and the Sloan Research Fellowship last year. So for us, it's a very, we are very happy that you accept the invitation to give us an online seminar on your last research. So thank you very much, Christine, and you can start.
Okay, thank you. Thanks very much for the kind invitation and also for the kind introduction. And I'm happy to have the opportunity to share with you now our new results. So let me share my screen. Right, so I hope you see my presentation now. Yes? Okay, so today I want to talk about measurement-based variational quantum eigensolver, on basically to give you an executive summary about this talk just up front. This talk, in a nutshell, basically is about hybrid quantum classical algorithms. It's about quantum simulations, studying interesting quantum systems by teaming up a classical computer and a quantum computer in a closed feedback loop. And the specific method that I'm going to address here is the so-called variational quantum eigensolver, and it has been very successful already. And these variational quantum eigensolvers are always circuit-based, or the existing method that you have on the market that people explored are circuit-based. And what I'm going to talk about here is a new variational technique, a different way to do this hybrid quantum classical algorithm, but not based on the circuit model of quantum computation, but on the measurement-based model of quantum computation. And the difference, in a nutshell, is that, of course, circuit-based quantum computation, you have entangling gates, you have logical gates, you have local measurements, and this constitutes your VQE, your variational quantum eigensolver. Well, what I'm going to talk about in this talk is, well, instead of entangling gate, you use the resource state, which is entangled, and you will see all the details in the next 30 minutes that we're going to talk together. But this resource state, I call it an efficient resource state because it's entangled, yes, but it's also efficient to make and efficient to determine, like how it looks like. And once you have this resource state, all you do is just local. You do local gates and you do local measurements. And actually it's completely up to you, the user, how you want to make your resource state. If you want to make it with gates, by all means, but you could also make the state in a completely measurement-based fashion. So if you like, you can do your whole computation just only applying local single unitary rotations and measurements. And this is a complementary approach to the known circuit-based VQE. And it's not necessarily the method of choice for every single problem, but as you will see, it has very different resource requirements. So for certain platforms and certain applications, so it has advantages. So it hence enlarges the toolbox of these VQE schemes. And to take a step back, to see it a bit from bird's eye perspective. So what is the vision or the aspirational goal here? Well, there's this concept of this universal one-way quantum computer, which has been introduced a couple of years ago. And what I'm talking about here is not this universal one-way quantum computer, but a one-way quantum simulator. Yeah, that's what we're exploring. And even more, a special purpose one-way quantum simulator. So be mentally prepared. I'm talking about devices that are just good for one specific type of problem. Like if you have one type of model that you want to simulate, you have this type of simulator. If you have a different type of problem, you will need a different type of simulator. And before I go into all the details, let me mention that this is a preprint where you can find more information that we put on the archive recently. And B, let me already highlight the people working on this preprint. So our first author is Ryan, who is just completing his master's thesis. And yeah, Ryan was working together with Luca Dell'Antonio, the postdoc on this process, on this work, and the two of them, they really pulled this off. They were the main people working on this, and we also, on top of our Waterloo team, we had amazing support from Wolfgang Dürr, our external collaborator from Innsbruck in Austria, and yeah, without Wolfgang, none of these things would have been possible, and Wolfgang is really a top world expert in one-way quantum computing. And of course, everybody in the author list contributed, but I just want to highlight really the contributions by these three people. Okay, so with this, we set the stage, we're ready to go. And here's an overview to the talk. I will start with an introduction to motivate you a bit and to explain what this is all about. Then I will give a quick overview about measurement-based quantum computing. It will be a very quick overview, just the bare essentials, what you need for sections 3 and 4 of the talk. I will present two schemes. I call them here just scheme 1, scheme 2, and then we will finish up with some conclusions. Okay, so here's the introduction. So everything that I'm going to talk about here is really about these variational quantum eigensolvers. And as I alluded to earlier, it really means that we have at the heart of everything a classical computer, actually. And the classical computer runs a classical optimization algorithm. And we, of course, know that if we do these variational schemes, if we have optimization algorithms on classical computers, we know that they, A, are very successful, but B, are also severely limited when it comes to the demanding task of simulating a strongly correlated quantum system. So what's coming in here is that the cost function evaluation is now evaluated on a quantum computer. So imagine you have a quantum coprocessor, and whenever the task to evaluate this cost function comes up, you're sending a request to your quantum device, and your quantum device basically gives you efficiently, in an efficient way, the cost function and feeds it back to the classical algorithm. So hence you access a larger family of variational states efficiently than you could do classically. I know this is all very brief. I invite you to look at this review that I linked there on the bottom of the slide. So basically, the very short version is that your quantum computer, you prepare an input state, typically an input state which is just a separable state that you can prepare with high fidelity. And then you have a certain ansatz wave function, which is parameterized. And so it has classical parameters in it. And these classical parameters are fed by the classical computer. And then you get an output wave function and you can measure on it and feed this back to the classical computer. And usually, especially for the type of scheme that we're looking at, the cost function is an expectation value of some algorithm. In our case, and it's a very prototypical case, we look at the expectation value of the Hamiltonian, of an Hamiltonian, so we measure an energy. and because we're interested in finding a ground state. Yeah, so we define a target Hamiltonian and say, oh, now we want to find the ground state. And this is, of course, a prototypical task for many applications. And we just minimize energy and finally find the state with the lowest energy, which is the ground state. And just one slide on how many applications you have and how successful this already is. It has applications in chemistry and particle physics, which is something that we in my group do a lot, apply these variational quantum eigensolvers to problems and lattice gauge theories, problems from high energy physics and particle physics. But you can also apply it to classical optimization, even sensing, and also many body physics. So it's a very versatile, generic, and mind you, very robust approach. Okay. Having said all of that, the models, as I said, are based on this circuit-based model of quantum computation, which is, of course, by no means the only one. Yeah, I mean, it's maybe the most prominent one, especially with now Google, IBM, and all the big companies jumping into this area. But we also know, well, there's a measurement-based model of quantum computing, there's adiabatic quantum computing, there's dissipative quantum computing, yeah, and in particular, here this measurement-based quantum computing is also capable of universal quantum computing, and is in fact equivalent in terms of scaling of resources to the good old circuit-based quantum computing. So circuit-based quantum computing, what tends to give us most of the headache is the size of the qubit register, especially in the NISQ area, where we era where we have like only these small-scale noisy quantum devices. Yeah, we would like to have larger qubit registers, and also can also tell you from personal life, a really big limitation is often the number of gates that you can perform, in particular the number of entangling gates that you can perform. In other words, the circuit depth is simply now today a limitation. And the reason why circuit depth is a limitation, it really is due to not only one reason, but really at least two. Firstly, there's an issue with coherence time, right? Like how long you can store your quantum information in your quantum memory in your qubit, but also the accuracy with which you perform your gates. Think about trapped ion quantum computers, for instance, one of my personal favorite. Yeah, if you have a trapped ion quantum computer, you basically have a perfect qubit. Yeah, I mean, the lifetime coherence time is much longer than what you actually need. But as soon as you induce entangling gates, you're the one introducing the errors into your system. It's like technical errors. Nothing is perfect, and you introduce errors while applying gates. And yeah, the more gates you apply, the more errors accumulate. And at some point, you will just run into a regime where the outcome of your computation is just overwhelmed and dominated by noise. Good. So my perspective on circuit-based quantum computation and some of its limitations. Okay, measurement-based quantum computing, as you will see in a bit more detail in just 5 minutes, is conceptually different. You take an entangled input state, and this entangled input state, you can, for instance, use a universal state like a cluster state, and then you make measurements on it. And the whole computation, as you will see, is performed by performing single qubit measurements. So the spirit is very different. Yeah, so in the circuit-based quantum computing model, you basically start with a product state, maybe start with 0, 0, 0, and then you build entanglement in your circuit by applying all your entangling gates. It's completely the other way around. In the measurement-based approach, you start with a ton of entanglement and you use it up, actually use it up. So this is why people sometimes call this also one-way quantum computer. It's a one-way story. Once you have performed your computation, you have destroyed your state, you have used up your entanglement. Okay, so what limits that? Several things, of course, but one major limitation is, well, the size of the entangled input state that you can prepare. So this is what you work with. That is what you can use up. And what I'm going to talk about like now is a new variational technique, is making a VQE variational quantum eigensolver, but now based on the principles of measurement-based quantum computing. And this is, of course, why we call it measurement-based variational quantum eigensolver. And as I said, the task that we address is to prepare the ground state of a target Hamiltonian. And the main idea, as you will see, is to use a tailored entangled state as a resource, a small custom state. We call it a custom state because it's custom for one type of problem. So it's not this universal measurement-based quantum computer where you have this universal state with which you can do absolutely everything. It's like you have one type of problem, you have one type of state, it's a custom state, and it can be much, much smaller. It can be much smaller than this big universal state. So this goes back to what I said in the very beginning. Instead of operating with this large universal cluster state, you go to a special purpose application with a small problem-specific state. And so in the next section, I'm going to show you two schemes, scheme 1, scheme 2. How are they different? Well, the scheme 1 is a direct translation. Suppose someone already has a circuit-based VQE. Well, you can directly translate it into measurement-based VQE, and I will also explain why you would like to do that in certain cases. Oh, and we do it for a concrete example because it's always best to see it at work, and our concrete example is applied to one-dimensional quantum electrodynamics. The second scheme is completely different, entirely different story. We call it state variation by edge decoration, so you will see why. And this really has no direct analog in the circuit-based model. It's like completely throwing the circuit-based model out of the window and doing something else entirely. So no direct translation. And I will also show you for a certain concrete example. And the example will be the toric code model. So, but before we can do that, let's quickly have a look at how measurement-based quantum computing works. So for those of you who know this, it's just a reminder. And for those of you who would like to dig deeper, I suggest especially the second reference here, which we use like a lot. All right, so on a measurement-based quantum computer, you can realize a universal set of gates, and this is what we're going to look into now. And the universal set of gates that I look at here is arbitrary single qubit rotations and a CNOT. If you have that, you can do everything. Okay, so let's look at the arbitrary single rotation first. The arbitrary single qubit rotation, if I want to, I can break it down into an XCX rotation with angles θ1, θ2, θ3. And this allows me to do a rotation about an arbitrary axis about an arbitrary angle. How do I do that? Well, in one way, in a one-way quantum computer, in a measurement-based quantum computer, I start with a resource state. And the resource state, it's depicted here. It consists of 5 qubits. And you can do it however you like. You can do it in a measurement-based fashion, but you could also choose to do it with gates, even though you don't have to. If you want to do it with gates, you prepare all your 5 qubits in the plus state and then perform a CC control phase whenever you have a link in this picture. Gives you an entangled starting state. So if you have this entangled starting state, let's assign different roles to the qubits. The first one is the input qubit. You store your input state there. Then the 3 guys in orange are ancilla qubits. They will help me to rotate about θ1, θ2, θ3, and then I will find my output state in the white qubit in the end. Okay, so how you do it, you apply measurements. You measure the first 4 guys, of course not the last one, because this is where you have the output state left. And you will have to follow the following recipe. The recipe is that you measure the first one in the X basis and the 3 ancilla qubits in a rotated basis. So the rotated basis is defined as you see on the slide in exactly this way. And you see if you set phi equal 0, it will be an X measurement, simply. All right, there's actually a catch, and the catch is that you need to adapt your measurement basis on the measurement results. So let's say the measurement results are S1, S2, S3, S4. That's what I get out of my measurements. And the thing is that if I have measured my first qubit, I got the measurement result S1. Oh, aha, S1 is 0. Interesting. Write it down. And then you go to your second qubit, and you have to measure it in a rotated basis. But the rotated basis depends on two things. A, it depends on what you just got out from your first measurement, but it also depends, of course, which rotation you want to implement. Yeah, this theta 1, that's the goal that you want to achieve. And then this goes on, yeah. So the second rotated basis, it depends also on what you measured before, and it depends on what you want to rotate. And finally, the third one also. Okay, now we have measured all these 4. We are left with our output qubit, and it's only almost what you want. It's almost what you want, yeah? Because you had your input state, you applied your unitary to it as you wanted, and you get a completely unwanted byproduct operator, but it's just a Pauli string operator, and also you know the Pauli strings, given you dutifully wrote down your measurement outcomes. And so, yeah, so it's easy to take care of that. Right, and this is what we call an adaptive measurement pattern. Adaptive because, as you just saw, it has to be performed in a certain order, and you have to adjust your rotation based on what you saw earlier. And well, not all operations are that way. There are also non-adaptive measurement patterns. So the so-called Clifford gates are non-adaptive, and these Clifford gates include, in particular, our C0 operations. It means all the measurements, you do them simultaneously or in whichever order you prefer. Yeah? So that's the resource state, the entangled resource state that you need for making a C0 operation, or the graph representation of this resource state. You see, it's a lot of qubits, and again, your task in order to make a C0, implement a C0 between 1 and 9, qubits 1 and 9, is you measure in which order you want, or all at once, all the blue qubits in X and all the orange, yellowish qubits in Y, and then you will get your output in qubits 7 and 15 with having your C0 performed. And with this, voila, you have a universal set. And tying into what I want to explain next is that we can concatenate measurement patterns. So the small, simple concatenation mini circuit. In this mini circuit, we have only 2 qubits, and there's this orange box where I want to rotate only around C. Yeah, I don't want to rotate around all 3 axes, just a C rotation, and I want it to be parametrized because that's what we need later on for our variational quantum simulation. And then I have a couple of fixed gates. So a fixed gate, like I have a Hadamard, a C0, and another Hadamard. And so here I have this cluster state, and in the beginning you see the 2 blue qubits are the input state, and then you see this color coding which shows you, okay, now you measure like there on the top in orange. So this is where you do your parametrized sigma C rotation, and it has only one variational parameter because, yeah, only in the C direction, and well, everything else is fixed, and then you get the output, and this is your circuit. And now there's a very useful Gottesman-Nil theorem which tells you, well, like the whole Clifford part, everything which is Clifford, which in our case is the 2 Hadamards and the C0, like literally everything else except the orange part, which is the sigma C rotation, you can perform classically efficiently. So let's just do that beforehand, actually. And then instead of doing all of the above, I can make a resource state which has only 3 qubits, yeah, which has one knob, I call it a knob, so it's one ancilla which is responsible for making the rotation, and by how much I rotate depends on which rotated basis I choose, and then I have my 2 output qubits, and then that's that's a much smaller state for having this one knob. And yeah, this already concludes the introduction, and I want to show you what we do with it. So So now it comes what I want to actually talk about. So the first thing is to translate a variational quantum eigensolver into measurement variational-based eigensolver. So I will first talk about the general idea, and then I will give you a concrete example. So the general idea is summarized in this picture. Suppose you have a circuit, and the circuit already solves your problem. You have a circuit-based VQE, and I color-coded here. Everything which is black is just Cliffords. Yeah, so it's Hadamard's, it's C-naughts, like it's fixed. And in between, we have these knobs, quote unquote, which are single qubit rotations. And now I can translate it, similar to what we discussed just a minute ago, into a graph state, which has already the Clifford part incorporated in it. And it has a couple of ancillas, and it has, like the ancillas, help me to do these rotations, and I make measurements, and I perform my whole variational quantum eigensolver, just like this. And this is, of course, useful if you have circuits with a large Clifford part, because this large Clifford part is then taken care of in the classically to get the smaller graph state. Yeah, I do not recommend it if you have a super small Clifford part and a ton of knobs, then of course the situation looks different. But let's look at a concrete example just to see it work. And one of my favorite examples is the Schwinger model. So it's quantum electrodynamics on a 1D lattice. We chose it, well, just because we work with it a lot. And also for applying quantum simulations for lattice gauge theories, and in particular this whole field of trying to apply quantum technology for problems in particle and high energy physics, it's a very good benchmarking model. Yeah, and yeah, I'd like to apply it to this benchmarking model here. It's in reality what it describes as electrons and positrons interacting via electromagnetic fields, but we're not going to worry about that. You can actually rewrite it and cast it as an effective spin model. So for our purposes, it's just an effective spin model. It looks a bit exotic. Yeah, it looks a bit exotic, but basically what it is, it's just a spin model with two body terms, as you can see, one body and two body terms, and it has a bunch of long-range interactions if you encode it in this way. This is what we're going to look at, and you can write down a circuit for it. Actually, several variational quantum simulations have been done for this model already very successfully. I mean, so also from my personal life, I had the privilege to work with an experimental team. It was a theory collaboration with the group of Peter Soller and with the experimental team of Rainer Blatt. And Rainer's team really implemented this with 20 qubits. So that was impressive. But yeah, so also people ran this on IBM. And yeah, this is something that the world has already seen in action. So there exist circuits for that. And here I depicted a circuit for you, which has this very typical shape that you make an ansatz, which gives you a layer, and then you repeat the layer over and over. And the layer consists, this is very typical, first you allow for single qubit rotation, and then you allow for something entangling. And then you layer it up like a good cake. Local entangling, and so on and so forth. So, and another thing that is like really a standard scenario, like if you want to run something on IBM, Google, or you name it, is that you have to break everything down in C-naughts and yeah, parameterized single qubit rotations. And well, this circuit just works. And you can also translate it. You can, like, using the strategy that I outlined earlier, you can translate it into a measurement-based VQE. So again, you start with an input state, and now our custom state, each of these layers, so each of these circuit bits are now a graph state. Yeah? And now you have a lot of ancillas and you measure. And what you already see, like these C-naughts disappear, and instead you have a graph state which is made out of, each layer is made out of 8 ancillas because you have 8 knobs. Like for each knob, you have an ancilla. And here are the results. I don't want to go into too much detail, especially because I almost used half an hour already. As we observed a quantum phase transition, and this quantum phase transition is one that is typically observed in this benchmarking system. So I plot here an order parameter versus a control parameter, and you can do it either circuit-based or measurement-based, and the message is that it just works in both cases, but the resource requirements are very different. So in the circuit-based model, you have a lot of entangling gates. So K is the number of layers that you need. How many layers you need is how close you are to the phase transition, or how much entanglement is in your state that you want to produce. If you're close to the phase transition, the state is very entangled, you need more layers. And this dictates how many entangling gates you need. The measurement-based version, you don't have entangling gates, but you have this input state, which is based on 2k plus 1 times s, where s is the size of the lattice, qubits. Okay, so what does this mean practically? So practically, if you have a platform like photons, for instance, and on photons it's difficult to efficiently do entangling gates, then that's an alternative, because you can do everything without the need to implement this long list, a long circuit depth sequence of entangling gates. And I can also comment on the required coherence time, which can be very beneficial if you have large Clifford gates and few knobs, but I will leave this in case there are questions in order to move on, and also have the opportunity to say a bit about scheme 2 in the last 10 minutes. So scheme 2, I will again outline first the general idea and then the concrete example. So that's a general idea. It's a picture made by Luca Dell'Antonio, who found this nice metaphor. And the general idea is that you start your search, because what is it? It's a search for a ground state, right? And you start your search in a suitable corner of the Hilbert space. And you do so by starting from an ansatz state. And the ansatz state is a problem-specific graph state. And then your classical optimizer searches, optimizes variationally locally in this corner. So matching this to this metaphor, basically, if you go on holidays, then you first take a long distance flight, which brings you to the correct corner in Hilbert space, to your ansatz, and then you walk on foot on your island that you chose, the Maldives, maybe. And so this is why basically you get the right entanglement structure. You get a lot of entanglement by already choosing a good ansatz state, and then you walk around and explore there. And when is this useful? So for example, this is just an example. Generally, it's always useful if you have a good guess. But suppose you have a Hamiltonian which has a perturbation. Then your ansatz state can be, for instance, the ground state of the unperturbed Hamiltonian, and then you explore in this neighborhood. And this is exactly what we do in our concrete example. The concrete example is the perturbed toric code. So for the perturbed toric code, if I have the H0 alone, the toric code Hamiltonian, of course I know the ground state, and of course it's a graph state and it can be determined very efficiently. This I know, I can calculate it fairly easily. Now I add a perturbation. Suppose on my quantum system there are fluctuating magnetic fields. So here fluctuating magnetic fields in C direction. Well, now the situation is different. So at least to my knowledge, or our knowledge, there's no known method for calculating the ground state under these conditions efficiently. So hence we employ our variational quantum eigensolver. And the ansatz state is our known ground state. So it's just a ground state of the toric code Hamiltonian. And so this is a graph representation, which you see on the bottom left corner. And now we need to explore. We need to allow our variational algorithm to explore there. And we do this by means of a custom state. It looks a bit messy, but I will walk you through now. So this custom state is basically what enables the measurement-based VQE. So basically this custom state consists of the answered state plus auxiliary qubits. So in our toric code example, you take your original state, and whenever you encounter an edge, you decorate it. What do you mean by decorating it? Well, you take 4 auxiliary qubits and you attach them as you see in this way. And I could tell you so much about ways to attaching them, because it's like you have so many options. Yeah? And like we attach them in this way because it allows to modify the entanglement structure in a certain way. But I will, in the interest of time, just gloss over it here. Basically what it does conceptually, you take your original state, and whenever there's an edge, you decorate it. So for instance, if you look at the bottom left 2 qubits, so you have something like this, and then you add these decorations, and like you do it like for every single one, and this is how you get this big messy state out of the small one. And then what the state variational protocol actually does, it takes these auxiliary qubits in this custom state, and they're measured. And what happens if you measure them, it modifies the custom state. I mean the state consisting of the qubits that are state left after the measurement. It's like applying a PWM in a sense. So, and the classical algorithm, which is at the heart of this variational algorithm, selects all these rotated measurement bases. And yeah, this runs in this closed feedback loop, and they're measured and selected in such a way that you minimize the total Hamiltonian, and then you gradually evolve, shape, and massage this custom state into something which very closely approximates the ground state. Well, and this is just the result. It's just to show you that it works. On the y-axis, you see the deviation of the energy over the actual energy. Is like how close to the true ground state you get. And we tried for several types of perturbations, which are drawn from a Gaussian distribution, for instance, or perturbations. Also, we played around what if a perturbation is especially strong on 1 qubit and not equally distributed about all. But so basically, bottom line, it works, and this explains state variation by edge modifications. And I want to conclude with that. I showed you 2 schemes. The first one was just a direct translation. Yeah, whenever you have a circuit-based VQE, you can make a measurement-based VQE, and it can give you advantages in terms of the feasibility and the coherence time if you have a circuit with a large Clifford part, and especially if you have a platform where you feel limited by the number of gates that you can perform. The second was an entirely different story, and it was a conceptually new way to construct variation families. It's really very different from the circuit-based model. And yeah, next thing we want to do is to find out how this can be experimentally explored. So this full toric code model that I introduced to you, it has 44 qubits, but you have by no means to start with something that big. You can look at a minimal instance. So instead of the toric code, we can look at the planar code, for instance. Or yeah, everything I showed you was for if you insist on having a deterministic protocol. But if you're saying, oh, for a proof of concept, I'd be happy to perform a probabilistic protocol, yeah, where just given a certain success probability and also have a success criterion, then you can go to much smaller system sizes. So Ryan and Luca just worked out one easy one with just 8 nodes, for instance. Yeah, and as I said, I find it extremely intriguing to open up these type of VQEs to photonic platforms. So in particular, there are these 2 very interesting papers from 2020, where we can see all the capabilities to make custom states, small custom states of photons in a very customizable way. And yeah, also in these other 2 papers, you see how the basic ingredients for these type of schemes already there, waiting for us to explore them. And other future directions, of course, will be very interesting to make detailed analysis to look at the noise robustness. Obviously, for this to be really meaningful, helpful, it will be platform dependent. Yeah. So we'd like to work this out for specific, to make a specific proposal for a given platform, and then really look into the noise robustness. And I can't wait to see how this will look like, because looking at the error thresholds for measurement-based quantum communication, it's a communication task, it's different, but it was surprisingly high. Yeah, so it can be as high as having a threshold of 10% or 23%. So amazingly robust. Yeah, so it will be interesting to see how it translates here in this context. And of course, it opens up a whole range of possibilities to explore these edge modification schemes. I showed you one edge decoration, but yeah, the possibilities are virtually limitless, and it's a new way to think about state variation, yeah, or how to design these VQEs. Because if you make an edge decoration, the effect after measuring these auxiliary qubits, it's not necessarily a unitary operation acting on your actual qubits, and also you may measure maybe only 1 or 2 auxiliary qubits, but based on your underlying entanglement structure, it may, of course, with one single measurement, you may affect many qubits at once. And yeah, it will be interesting to make new schemes of that. And yeah, with this brings me to the end, and I'm closing the loop here. It started from looking at the universal one-way quantum computer, which uses large cluster states input, and now here we're looking into special purpose one-way quantum simulators, which deal with small problem-specific states. I want to thank again the people who did most of the work here. Big thank you to these 3 amazing guys. And I want to thank you who just watched this. Thank you for your attention. And yeah, I'm also happy to acknowledge support by these funding agencies who allowed us to do this work. We also have positions available if you want to come and do research with us at IQC. And yeah, that's it for today. And I'm looking forward to your questions.
So thank you very much, Christine, for the nice talk. So yeah, I'm going to read you some questions that appear in the chat, okay? So the first question from Fernando is, what are the strengths and weaknesses of measurement-based quantum computing with regards to the circuit-based code?
Yeah, strengths and weaknesses, this depends on so much on which platform you want to do it. One weakness, for instance, is, okay, it depends really on the platform, but I suppose, for instance, you're an atomic physicist, I want to do it with atoms, I want to do it, or maybe with ions, and then I have a system on which measurements take very long, yeah? So that would be, for instance, a weakness. Yeah? I would like to go to a system where I can do measurements really fast, especially if I want to do a variational quantum eigensolver, which is heavily measurement-based. Yeah? Another weakness is, again, platform-specific, but suppose I want to do it with photons now. Yeah? So these adaptive measurement, it really depends on how many you need. But if I have a lot of adaptive measurements, yeah, so I have to store my photons or keep them coherent while measuring the previous ones, because I need these results in order to faithfully perform the whole sequence. Yeah, of course, and for instance, superconducting qubits, which also have fast measurements, so this would not be a big issue. Yeah, so it's like very platform dependent. Okay, strength of measurement-based quantum computing, not necessarily VQE only, but like really in general, is that we have seen for several that we have seen for several applications these extremely high error thresholds. Like when I saw these thresholds the first time, I thought, oh, this is a typo. Yeah, so this big robustness that have been demonstrated is a big plus. Yeah. And then later on, I could name more advantages, but these are then application dependent, yeah, for certain problems. Like for me personally, I think it's nice to have like a really complementary toolbox to, depending on what platform you want to use and depending what problem you want to address, that you can pick and choose whatever works best.
So this is mine, because I don't know if you told during the talk, but the plots that you saw with the points are numerical or experimental?
Numerical, like it's brand new. We just did the theory on that, so we have absolutely nothing experimental on that. It's all purely theoretical, and actually it will be our next step to look into experimental realizations. So there has never ever been a measurement-based variational quantum eigensolver experimentally. I mean, this is just the first proposal, and we literally just finished it, and we just put it on the archive just a short while ago.
And how did you compute this? So you compute by simulating the quantum circuit. You include errors, or how do you do the simulations?
This is the ideal calculation. So the errors will be the follow-up project, basically, that one picks a system, then looks at, oh, what are the errors that we have to expect in the system, and then do the whole thing again. But no, not the ideal case, but the realistic case.
Okay.
So this is just the ideal case. It's just the concept, basically. Okay. And completely, like whatever I talked about today, it was just the idea completely in a platform agnostic way.
Okay. So there is another question from Fernando. I imagine this method might be better adapted to certain experimental platforms. What are the ingredients, if any, that determine which approach, gate-based or measurement-based, will give best results? Fernando is an experimentalist.
So what was the last part of the question?
Yeah, sorry. So at the beginning I imagine this method might be better adapted to certain experimental platforms. Mm-hmm. So the question is, what are the ingredients, if any, that determine which approach, gate-based or measurement-based, will give best results? So if you can imagine in advance which one it's better, or
yeah, it depends both on platform and problem. But if I have a platform, okay, let's suppose I have a platform. I can think of two scenarios. Okay, let's say I have a platform like photons, for instance. Yeah, doing large gate sequences with photons is challenging, right? Yeah, and if I have on top of that a problem which allows me, like the problem consists of a large Clifford part and just some knobs, right? Then I would completely alleviate the necessity to do all these CNOTs, right? Because these CNOTs would basically just go into my initial starting state, which I can do in a which I can prepare however I want. And for this photonic platform, I could then I can foresee that I could perform VQE in a measurement-based fashion, which I could just not implement otherwise, for instance.
Okay.
Or if I'm limited by my coherence, if I'm able to do measurement fast and I'm limited by my coherence time, that's another example. Because the coherence time can be much shorter for the measurement-based approach, because the point is the coherence time, it will only depend on the number of knobs. Yeah. So that's the only thing that determines the coherence time here. So even if I have like a large circuit, yeah, and it has few local rotations and it has a lot of CNOT operations, yeah. So if I do it in a circuit-based fashion, like the number of CNOTs that appear will totally feed into my need into my need to have a coherence time which allows me to sustain all these C-naughts sequentially. Yeah? Whereas if I go to the measurement-based approach, it's all condensed in this single input state. And in this single input state, how it can be prepared, it has a circuit depth of 1. So in other words, if I were to make it as a circuit, then it would be like everything at once. Or if I do it in a measurement-based fashion, all measurements can be performed simultaneously. Yeah, it's a constant time. So if I have a problem which has a large Clifford part and only few knobs, then it's advantageous to use the measurement-based approach, because the measurement-based approach in terms of coherence time depends only on the number of knobs.
Okay. So this is another question from Carlos. Do standard error correction codes work in this context?
Well, I could directly translate it, I guess, because I can translate everything back and forth. I mean, I could, but I wouldn't. Yeah. I mean, everything I do can be translated back and forth, and it's in principle equivalent in terms of resources. It will look very different practically, but yeah, I think one would have to go for a measurement-based version of quantum error correction. So one would have to rethink that.
So let me read, because this is long, so let me try to understand first.
Okay.
Yeah, so Juan, ask, I mean, you need some answers, right, to start with. So
yes.
Essentially it's kind of model dependent or problem dependent,
yes.
right?
Yes, it's problem dependent, problem specific, absolutely.
So yeah, so you need an answer to start with. So this is clear. So this is a mandatory.
For scheme 2, for scheme 1, I don't need it. Yeah, I mean, scheme 1, I don't need any answers, but for scheme 2, that's the whole idea. It's often how we solve problems, now that we have a guess. Yeah, or if you have a Hamiltonian with a perturbation, then the unperturbed Hamiltonian naturally gives you your guess. That's in the definition of your problem, basically. But yes, you need the ansatz. You have to have a clue.
Yeah, but now it's my my question. But now even in the first part of the talk,
the direct translation.
Yeah, you need to. I mean, you want to explore over some wave functions in order to find. So you cannot be quite far away from the real solution, right? So you need to start with a good starting point.
Yeah, in scheme 1, you can actually start as far away as you want. Yeah. So but now we are talking about variational eigensolvers in general. No, I mean, regardless whether you want to do them with a circuit or measurement based. Yeah. So I didn't cover this so much in detail in my talk, but basically you always make an ansatz, and this ansatz is an ansatz wave function. And in the circuit-based model, the ansatz is basically the circuit. I think I'm still sharing my screen.
Yes.
So yeah, so where do these parameters go? And yeah, this is what you typically do. You make a layer. And so the ansatz wave function is just, you have your initial state, which is always something simple like 0, 0, 0, plus, 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 plus. And then you just apply entangling, local, local, or you can make a custom ansatz, like it's completely up to you. But this is like your ansatz wave function, and it has some knobs where you can tweak, right? And this ansatz is always there. This is just how this variational quantum eigensolver works. That's its underlying working principle. It's
but
a state family that can, a variational state family. You can call it a variational state family.
But I guess that the amount of wave functions that you can explore depends on the number of layers. For example, this capital K here.
Yeah, absolutely. And also the amount of entanglements that you can pack in. Mm-hmm.
So as far as you can increase the number of K, you can explore more the Hilbert space, and you are more, let's say, sure that you are going to reach a good ground state, right?
Yes. Also the type of gates that you allow. Yeah.
Also the type of gates, yeah.
Yeah.
So the last two ones, okay. So is it possible to use this variational procedure for computing excited states?
Oh yes, absolutely, and we totally do that. Yeah.
Okay.
Yeah, exactly. This is what I'm going to do right now after my talk. Yeah. Yeah.
How?
And we have also, if you look at our 2019 paper, Coherence is the first author, so we also we accessed excited states in the Schwinger model. Yeah.
Okay. And yeah, so this last question is, what kind of problems are interesting to look at from this point of view in the context of particle physics?
Oh yeah, all sorts of problems. Like we start with the Schwinger model because we know what happens. It's a benchmarking model, but it's also not yet where we want to be, right? So this whole field is in kindergarten. The whole field is a toddler basically taking its first steps. Because the big vision is, of course, one day we want to understand nature, right? So we want to simulate nature and hopefully one day tackle problems that cannot be tackled with classical computers, that cannot be tackled by Markov-Chain Monte Carlo, right? I want to tackle sign problem afflicted problems. I want to do time evolutions. I want to do, I solve problems with, so-called topological terms. I want to solve problems with high fermionic density, like everything that classical computers cannot do. And of course, I need to go to 3 dimensions. So more important, so interesting models to study. So to go from the Schwinger model, which is 1-dimensional, to go to quantum electrodynamics in 2 dimensions and then in 3 dimensions. Yeah, then you can also add flavors, for instance, a Schwinger model with flavor to make it even more interesting. And then another extremely interesting direction is to go to non-abelian gauge series. So of course here quantum electrodynamics is a abelian series, the photons don't interact with each other. Good for getting started, but of course it gets even more interesting if you have color degrees of freedom. And of course, if you want to simulate nature, one day to go towards QCD, we need to be able to simulate a non-abelian gauge series. So of course, SU3 would be extremely interesting to look at, but it's also 3 colors at once. No, so something that we can do as a first step is to go SU2, just 2 colors. SU2 with just red and green. Yeah? And there are a lot of models. So now I named all them. There are even more and more, right? Models in high energy physics, but there are also lattice gauge series which are then also interesting in the context of condensed matter physics. For instance, if I add topological terms, so Schwinger model with topological term or similar. Yeah. Oh, and there are excellent reviews on this also. Marie-Carmen Barnolds, for instance, first author, with her, our whole big collaboration, published a review on this just recently.
Okay, so there are a lot of problems. Good.
No shortage of problems.
So thank you very much, Christine.
Thank you.
It was a very nice talk and it was a pleasure. Again, thank you a lot for accepting the invitation. And we let you to continue with your calculation with excited state now. Yeah, so thank you very much, Christine.